Okay, so let us continue from the previous video. So, we were actually discussing the transition matrix, and for that we need all 14 states. So, for reference I am actually making in the corner, so that this can be referred back and forth again. So, quickly just writing it down, it is a state 1, state 2, this is state 4, state 5, six, seven, this is state 8, So, these are the 14 states which were we had been referring to. So, coming back to the state transition table. So, I had, so we will keep on filling. So, if you want to remain from state 1 to state 1, and this particular transition table we call it at the jth stage transition table type 1, and this actually means going from m is the row id and I is the next state to which you are actually moving in the jth stage. This is the probability for that. So, if you want to remain from 1 to 1, if you are in state 1 you will surely will remain in 1 only, there is no other option. If you are in state 2 you will go to state 2 if there is no packet going out. So, you call it qj tilde, and if the packet goes out you come back to the state 1. So, from 3 if you can want to go, you can actually, if both the packets moves out you come to state 1, if only one of them goes you come to state 2, and if both of the packets do not go, from state 3 you will come back to the state 3 only. So, from the fourth one, so the fourth state is this one, there is no packet at the output. So, you are going to remain in the same state because there is no packet which can go out. So, in the fourth you will remain in the same state. Okay. The fifth state, if you look, there is one packet, it can go, it may not go. So, with probability pj tilde you will be coming to state 4, and with qj tilde you will remain in, go to the 5. Okay. So, similarly I can keep on doing it. So, sixth state, again you can look there, there is only one packet which is present, it can go out, you can come back to the fourth state, otherwise you remain in sixth. So, in the 7th state there are 2 packets. So, if both of them goes out, you come to 4. If the upper one goes out, in that case you will end up in 6. If the lower one goes out, then you end up in 5. So, and if none of them goes out, you will end up in the same state, which is 7. Okay. So, similarly for 8, I can write down. So, 8, if you will see that there is no packet at the outgoing ports, so it will always remain in 8 with surety. With 9th state, again there are no packets, it will remain in the 9th state. Since a sparse matrix, rest all elements are 0, so only certain elements, so I am just filling up those. If you are in 10th state, if the packet goes out, you go back to 8. If packet does not go out, you go to 10. Okay. So, with the 11th state, let us see what is going to happen. There is only one packet out. If the 11th packet goes out, then you will get into 9th state. Packet does not go, you remain in 11th state. And the 12th, let us see what is going to happen. The 12th, there is only one packet which is at the top. So, if it goes out, you will end up in 8, otherwise you remain in 12. The 13th, if both of them goes out, Pj tilde square, else Pj tilde Qj tilde for 10th, or you will end up in 12th state, Pj tilde Qj tilde, or you will end up in 13th state, Pj Q tilde square. For the 14th state, you will be Pj tilde square, with that you will remain in 9th state, or you will come back to go to 2 Pj tilde Qj tilde for 11th state, or you will end up in the 14th state itself, Qj tilde square. Okay. So, that is a transition matrix for the when the packet will go out, it is basically after step 1, okay, in state J. So, once you have this, you can actually find out after step 1 the probability that the switch in jth stage will be in state I after step 1 in time interval k will be given by summation of m goes from 1 to 14. This was the probability that you are in mth state after 0th step or at the beginning of the interval in jth stage, and of course your switch goes from M to I stage as per this transition matrix. So, you have to compute this transition matrix. So, Tj elements. So, these Pj's tilde and Qj tilde will be depending on the state probabilities of j plus first stage. Okay. So, in this case now 1 less than equal to I less than equal to 14, this is how the I will be iterating. Okay. Similarly, we can actually build up a matrix which will be for stage 2. So, we call that matrix as Tj2. Okay. So, let me put it here and we will just fill up the entries again. The matrix so this will also correspondingly will change. So, this is the matrix, this will be after step 2, okay, transition matrix after step 2. So, if you are in state 1, so this transition matrix allows the packet to actually move to the second to the from input to output in state j. So, if you are in state 1, you will remain in state 1, obviously there is no other change. If you are in state 2, you will remain in state 2, okay. You are in state 3, you will remain in state 3. You are in state 4, then your packet actually will move to the output side and you will come to state 2, okay. So, from 4 you will be able to come to, so this is a probability, sorry, this is a transition probability, so which is 1. So, with probability 1 you will be coming to state 2 from 4th state. From 5th state there is no possibility, 5th to 5th you will remain. From 6th state you will go to the state 3, okay, and from state 7 you will remain in state 7, there is no change. State 8, if you look, there is only one packet which will go on that side and you will end up in state 5, okay. State 9, if you look, both the packets will go to the output side and you will end up in state 3. State 10, so if you check from here you will remain in state 10, so 10 remains in 10. State 11, if you look, this packet will move to the output, so you will end up in state which is 7. So, 11 to 7 will be their transition. Okay. And then state 12, if you look, there is output is empty. So, one of the packet will go there. So, any one of them actually can go on that side. So, you will end up in same state as 7. So, 12 to 7 there will be a transition. (13) you will remain in state 13 only, no change, and state 14 you will remain in state 14 only. So, that will be happening after step 2. So, once you know this, you can actually find out if you know what was your, I can now build up a transitions based on this. This will be P2. This is a probability after step 2, what is the chances that, what is the probability you will be in state 2 in kth time step. This will be summation of m is equal to 1 to 14 P1 mj okay, this is the probability after step 1. So, once you know this, you know the transition probability, you know what is the chances of being in state I after step 2. So, you can actually write Tj to Mi, and this is what is going to be used for this one. Again in this case I will go from 1 to 14. Now, there is a third step which will be happening, which is when the packet will be arriving at the input. So, we can actually build up a transition matrix for that. I call it Tj3 and let me fill up. Now, we will be writing Pj bar and Qj bar as the elements here, again using same strategy. So, if you again look at the state. So, if you are in state 1, there is no packet which is going to arrive at the input. Okay. So, you have to look at the arrival probability. So, both of them are free if there is no arrival. So, Qj bar square you will remain in state 1. If only one packet arrives which is having probability of 2 Pj bar Qj bar, in that case this will end up in a state 4. If both of them arrives, then you will be actually in state either 8 or 9, one of the two states you will be there. So, correspondingly we can actually put up the values. So, it will be Qj bar square, remember it is a bar this time now for the third matrix, and you will come to the fourth state if you have put Pj Qj bar, and of course with 8th and 9th state you will be going with half probability, actually half of Pj bar square, half of Pj bar square. Okay. So, if you are in state 2, then what is going to happen? You can get in that case no packets, so you will remain in state 2. So, if you are here, there is only no packets arriving. So, with Qj bar square you will go back to the same state. Okay. If there is only one packet is coming, so you may actually have two choices here. You may get a situation where the packet, only one packet is coming. So, either packet comes here, it does not come here, okay, and this packet can be uniformly directed to either this case or this scenario, these two. Other case is the packet actually comes on the other side and it can be directed on this side or other one. So, that possibility is this actually. So, you can actually see these two cases are same, equivalent, these two cases are also equivalent. So, with half probability this will be happening, with half this will be happening. So, this corresponds to state 5 and this corresponds to state 6. Okay. So, we can now correspondingly put the values. So, Qj bar will happen, you will remain in same state. With 5th and 6th you get Pj bar, Qj bar, Pj bar, Qj bar. Now, there is a problem when two packets will come, so then it is slightly tricky. So, let us see what is going to happen if there are two packets arriving. So, we are talking about state 2, state 2 is this. So, there are two packets which are arriving, so it is a Pj bar square the probability, but in which all states I can move. So, these both can be directed to the same port, the upper one. So, this can go to this scenario this can go to this scenario, and this can happen this one, and you can have a scenario like this. Okay. So, these all 4 can happen with the equal probability. So, this will be happening with Pj's bar square 1 by 4, this will be happening with Pj bar 1 by 4. Now, these two are technically same. So, I can simply write it as 1 by 2 Pj bar square. So, this one is a state this one is state 11. You can see from here this one is state 12 and this one is state 10. So, 10, 11 and 12. So, we have to write the corresponding values. So, it will be 10 will be 1 by 4, (11) will be half Pj square and 12 will be 1 by 4 again. Okay. So, similarly now moving over to the third one. So, with third one we are talking about this particular state, and let us see the scenarios which happen in this case. So, there are 2 packets which are there at the buffer. So, I may not get any packet. So, with Qj bar square I will remain in the same third state. Okay. If there is only one packet which is coming, so this will be directed to any one of the ports. So, with 2 Pj bar Qj bar you will end up in a state which is 7. And if when 2 packets are coming, then what is going to happen? If 2 packets come, you will have a situation when both of these are directed to 1, okay, they can be directed to this scenario, they can be directed to parallel, or they can be directed in a crisscross manner. So, these two are same states, these two are the same states. So, it is half half. Okay, so, 13 and 14 and they actually belong to 13 and 14. Okay. So, same I can do now with 4. The fourth state is this. So, fourth state, let us see what is going to happen. There is only one packet which can arrive, and that packet can be now directed to, if there is no packet arrival you remain in 4 states. So, that is Q. Okay. And the other packet which arrives, so there is only one packet which arrives, this can be directed here or this can be directed parallelly. So, it is half half. So, I have to write here this is 8 and 9. Okay. So, now similarly I can do it for 5. So, in fact more or less now it is straightforward. The fifth one you will remain in state 5 if there is no packet which arrives, if the packets arrive in the fifth state, this can be directed to this or this with equal probability. If it is directed to this, it is half actually. So, this turns out to be case number 10, and if it is not, this case number 11. So, it is between divided between 10 and 11. So, it is half of p j bar, half of p j bar. Okay. So, sixth, if you look, sixth state is this one. There is only one packet which can arrive. This can get directed to this or this with equal probability. If they are both directed to this, you actually have got 12. If they, and if this is directed to this one, then you end up in 11. So, 11 and 12 basically will be there. So, 6 will remain in 6 with q j bar. With the 7th, similarly, I will remain in 7th state with q j bar, and 13 and 14 I will do half half of p j bar actually. Okay. Then we look at 8th. So, there is no possibility of packet coming in, you will remain in state 8. 9 is same, 10, 11, 12, 13, 14, all of them will be unity. So, 8 always remain in state 8, 9 will remain in 9, and so on. And this is the last state which will also be unity. Okay. So, this is the last matrix, and based on this I can actually estimate what is P 3 I j. This incidentally also is equal to P 0 k plus 1 I j as per the way I have defined. So, this I can write down the equation as m goes to 1 to 14 P 2 m j in step k T j 3 m I goes from 1 to 14. Okay. So, once you have this, I can actually keep on I can actually use these p zeros which are there to estimate at any stage what is the probability that a packet will be available at that port. Okay. So, packet availability can be written now, we will be requiring this again. So, I can erase this and write down the equation. So, probability that the packet will be existing is defined by p j at stage j, and this probability will remain same for all output links of the stage j, all switches. So, this is probability that a packet exists at an output link of a switch in stage j at time, in fact Tk, that is when the interval will start. So, this value will be nothing but, so basically I will just look at what are the state probabilities at time in step 0 basically. So, I will be using P 0 and the various states. So, when you are in state 1 there is no packet at the output link, so this cannot be there. With half it is going to be there if you are in state 2. So, I can write down this half P 0 2 j k. So, the third one, there are two packets. So, with there will be actually two terms. So, one which is with half, other one without half. So, this will be P 0 3 j k. The fourth one will not be there, fifth one will be there with the half, and similarly the sixth one will be there with the half. The seventh one will be there with full, and eighth it will not be there, ninth it will not be there, 10th will be there with half, 11th will be there with half, 12th will be there with half, '13 and 14 will be there with full. So, that is the probability that a packet will be existing. So, this will be required to essentially estimate the sequence. So, we will be using two boundary conditions once we have all these equations. I can now erase these equations, you have to remember it for computational purpose. So, our boundary conditions which will be there will be P n minus 2 tilde will be equal to 1.0, packet is immediately emptied the moment it goes to the output link of the n minus second switch, n minus second stage switch. Arrival is a maximum loading condition, packet is always available, these two has to be used, and initially you assume that there are no packets anywhere, 0 packets in the network. So, and of course, you also assume the initial condition as P 0 at the 0th time step in the beginning, 1 j. So, you are always going to be in state 1, okay, for all stages, for all j this will be equal to 1 to begin with, and of course, P 0 in time step 0, all other states for all j and m greater than 1, it is not equal to 1. So, for all other states it will be made 0, that is the initial condition when you have to do the computation. So, what you do is using this actually you will find out what is P 1 m j 0, you will be doing it for all values of m. So, you already have after 0th step, so based on this you compute what is going to be there after the first step, and you will be doing it for all j. Okay. So, for all j's you will be doing, so from there you will be now computing P of 2 0 m j, again this will be done for all n j's. From there you will be now doing P 30 m j for again all values of m and all values of j, and from there this is nothing but this will become your P of 0 for step 1 now, m j this will be fed here, and then the next iteration, next step will be happening, you will iteratively keep on computing. So, ultimately all your state probabilities they were actually taken to be 0 in the beginning, this will start building up, and ultimately you will get a steady state situation in your computation, and once you have that you can actually from there get these particular probability P j which will give you the throughput. So, if you know P j you can compute P n minus 1 and that will give you the throughput on that particular line. Okay. So, but when you should actually stop your iteration, that still remains as a question. So, normally the way it should be done is, this is the probability that a packet will be there on a line, and this is the probability that packet is going to go out. This is a conditional probability. So, packet is there and it is going to go out. When this value becomes relatively constant, so your computation would have been stabilized at that point of time, and this should become stable for all j. Okay. So, for all stages same average number of packets is going out, this will remain constant irrespective of j. So, P1, so this actually means among your stages. So, if you look at the first stage, your value of Pj or P1, P0 in this case will be higher, okay. And what will happen, because this is higher, Pj tilde will be lower actually in this case. As you go to the next stage, P of 1 will be actually lower, but P1 tilde will become higher. So, this actually will start growing and this will be reducing across the edges, but their product will become same, and that is what should be observed in your computation, and that is when you should you can stop your computation and then use that estimate to estimate the throughput. Okay. So, once you have this, so you can actually find out what is your P of n minus 2. Okay. So, that will give you the throughput, and total number of ports will be 2 raised power n. You can find out what is the total delay, normalized delay. This will give you the total throughput of the switch. So, that is how this actually computation, this whole model can be used to estimate the performance of the buffer delta.